Okay, here's the start of the swimming pool problem. Word 1. There's the problem. We got this swimming pool that has a side view that looks like this, which is a trapezoid. This is 12 meters. This is 3. This is 1, the shallow end and the deep end. And then if you can visualize the pool going this way, it's 6 feet deep. By the way, this is a poorly stated problem. There is 1 meter of water at the deep end. Really should say the depth of the water at the deep end is 1 foot. Here's kind of what the picture looks like. There's the amount of water that we have if there's 1 foot in the deep end. Here's what it looks like on Ysant. I'm sorry, on Desmos, where A is this distance right here, or the height, I'm going to call that. As the water level increases, the amount of water in the pool increases. Initially, there's no water, 0. So as we start filling up, we want to know if we're pouring 1/6 of a cubic foot of water into the pool continuously. When the height of the water at the deep end is 1 foot, how fast is the water level increasing? So we're going to talk about that. But part A deals with what percent of the pool is filled when there's 1 foot of water in the deep end. And we talked about the fact that the total capacity of the swimming pool is the area of the trapezoid, which is this base. I'll draw it again. 3, a base of 1, a base of 3, and a height of 12. That's a cross section of the swimming pool. And the area of that base, the area of a trapezoid, is the height times the average of the 2 bases. So the area of this base is 12 times the average of 1 and 3 is 2, 24. That's the area of this base, 24 square meters. And if we multiply that by the height, this is like a trapezoidal prism, we'll have the volume. The total volume is 24 times 6, or 144 cubic meters. Now the question is, let's go to board 2, how do we find the volume of the water when the water level is 1 foot deep? This is 1 right here. Well, we need to find out what this distance is right here. And one way to do that would be to write the equation of this line using point slope. Another way to do it is to realize that we do know this distance is 12, and we do know that this distance is 2. So the big triangle here is similar to the little blue triangle. So we could say, if we call this x, 12 is to 2, using similar triangles, as x is to 1. So x equals 6. So the area of this little blue triangle, that's a triangle. And it's a right triangle. So 1/2 the base times the height. 1/2 of 6 times 1 is 3. 3 times 6 will give us the volume. So the volume of the water when the depth is 1, water when h equals 1 is, again, 3, this is a 6, half of 6 is 3, then 3 times the height is 18 meters cubed. So the percentage is 18 out of 144. See if I did that on Desmos. 18 out of 144, there it is. The volume of the pool is 144, the volume of the water is 18. Water volume divided by pool volume is 12.5%, 1,844ths. So this is 0.125 or 12.5%. So that's the answer to part A. 12.5. Now to answer part B, we have to have a formula for the volume of this water right here as H increases. So if I go back to here, and I called it A here, but we want the volume of this blue water depending on H, or A as I called it on Desmos. So let's go to board 2. I'll erase some of this stuff. Now we're going to make the assumption that we only care about the volume of water when the water level is 2 feet. We're trying to find out what, I'm going to call this H right now. We're trying to find out dH dt when H equals 1, essentially. So if this is H, and I redraw this right here, this is 12, this is 2, this is X, this is H, then the relationship is 12 is to 2 as X is to H using triangle similarity. Or 6 equals X over H, or X equals 6H. Why am I doing that? Because I want a formula for the volume in terms of H. So the volume of water, this blue water right here, is the area of this triangle times 6. So the area of that triangle is 1/2 of H times X. Oh, this is supposed to be 6H. Is 1/2 of H times 6H, that's X. That's the area of the blue triangle, but then I have to multiply that by 6 because we have a prism, and the height of the prism is 6. So there's a formula for the volume of water in the pool as long as H is less than 2. So that becomes half of 36 is 18H squared. And when H is 1, we do get a volume of 18, which is what we had on the previous board. 18 out of 144, remember? So now we can take the derivative with respect to t. This will be 36H times dH dt. We're supposed to find out how fast the water level is increasing when H equals 1. And we're told that dV dt is 1/6 cubic meters per minute. And H is 1 meter. And we want to solve for dH dt. So basically, I just have to divide both sides by 36. So 1/6 times 1/36 equals dH dt. And 6 times 36 is 216. So the water level is not going up very fast. That's meters per minute, 1/216th of a meter every minute. There's your answer. Okay, there's other ways to do this, not using similar triangles. I could write the equation of this line using point slope, or slope intercept even. The slope of that line is between 0, 0 and 12, 2 is 2 minus 0 over 12 minus 0, or 1/6. And so y equals 1/6x plus 0, the y-intercept. So there's a relationship between y and x, between h and x. Y is 1/6, or h is 1/6 of this distance right here. Now if we needed a formula for water level, when we got clear, water level got clear up to here, and we needed a volume formula, we'd have to create a piecewise function, and it gets pretty ugly. So I'm sure the problem was just intended to find the volume of formula for the volume of water as long as h was less than 2. There you go. Hope that helped. We'll talk about it if you still have questions.